Alright, this is the second video in a series called What Every Programmer Should Know About Memory. Just turning that into an acronym, WEPSKAM. And we're on page 5. I debated what we should title this video, Gate Level and Access Protocol, or Types of RAM and Intro to Access. Either title will work. I think the first one just sounds a lot cooler though. So at the top of page 5, he says, the following two sections discuss hardware details at the gate level and the access protocol between the memory controller and the DRAM chips. So I figure a good question would be, what two things will the access protocol connect? The answer is the memory controller and the DRAM chips. Since the target audience here is programmers, not necessarily hardware people, he will say, Drepper that is, will say programmers will likely find the information enlightening since these details explain why RAM access works the way it does. So let's skip the first part there and jump down to why there are static and DRAM types of RAM. If static is so much faster, why would we ever use DRAM? Well, not surprisingly, cost. SRAM is more expensive to produce and to use. So in today's video, we'll be getting really into the low-level details of the implementation of the concept of RAM. And here's a much bigger picture of SRAM. You have 4 transistors in the core here, and then there's 2 transistors on the side, M5 and M6. And these will work as long as there's constant power to VDD right here. And since I'm on the picture, I'll go ahead and just kind of speed through what that text will say. In order to write to this line, you would set BL and BL inverted. This is an answer I put on Stack Overflow actually. See, there's my little picture guy. And I think I summarized what Drepper was trying to say by showing this diagram there. But make sure you're walking away with the big idea that these cells have 2 stable states. It's either a 0 or a 1. If I go down here to a DRAM cell, DRAMs are built on capacitors. So here's our capacitor. So the transistor comes into play when you want to read or write. This is the access line. So you raise the access line in order to read or write what's in the capacitor. Capacitors are a little tricky though because they will constantly lose charge. This is the term they call leakage. So that means these capacitors have to constantly be refreshed. Doing so takes time. So part of the reason SRAM is much faster is because the state of the SRAM cell is quickly available. All you have to do is access the word line. At first I thought that was the write line because you access it or raise it in order to write, but you also do it to read. Just don't forget it's called the word line. So I think it's worth your time to answer this question. How many transistors are in SRAM? How many transistors are in DRAM? Let me scroll to the top here to make sure we're not missing anything. If the cell state must be overwritten, the BL and BL inverted lines are first set to the desired values, and then the word line is raised. Since the outside drivers are stronger than the 4 transistors, this allows the old state to be overwritten. And I guess I'll go into more detail later on how cells work. But let's read a summary. One cell requires 6 transistors. There are variants with 4 transistors, but they have disadvantages. So this must be a summary on just SRAM. I got ahead of myself by explaining DRAM to you a little early. The second note here is maintaining the state of the cell requires constant power. The cell state is available for reading almost immediately once the word access line is raised. And then there's some details I'll go into in another video because I have better graphs for us to look at to internalize what they're saying right there. So we'll finish the SRAM section by saying that the cell state is stable. No refresh cycles are needed. Alright, so all a DRAM consists of is 1 transistor and 1 capacitor. This is a huge difference in complexity, of course, and it means it functions very differently than static RAM. That last sentence they didn't need to write into there. Come on, Drepper. I should not criticize this writing though, because it's really excellent and helped me tremendously. Alright, well, to write to the cell, the data line is appropriately set, and then The access line is raised for a time long enough to charge or drain the capacitor. There are a number of complications with the design of dynamic RAM. The use of capacitors means that reading the cell discharges the capacitor. The procedure cannot be repeated indefinitely, and the capacitor must be recharged at some point, even worse to accommodate a huge number of cell chips. So we could be talking about chips with 10 to the 9 or more cells. The capacity to the capacitor must be low. They're talking femtofarad range or lower. And if you think about it, a fully charged capacitor only holds tens of thousands of electrons. That's not very much. So the idea that these electrons are leaking out is called leakage, so you'll have to refresh it. And Draper says that happens about every 64 milliseconds. And I recently changed out my air conditioning capacitor, so I was wondering how it compares to such a large, very large capacitor that I just put into my AC unit. Well, let's get a question here. What is leakage? So don't forget it's a type of problem here. But there's more than that as a problem. There's a second problem resulting from the tiny charge that the information read from the cell, it's so tiny it's not usable. So thus that DL data line must be connected to a sense amplifier which can distinguish between 0 or 1. Now there's a third problem, but I'll just skip down here to read. It says it does mean, though, the reading memory content requires additional energy and, more importantly, time. So that's the third problem. The refresh is happening automatically, and this is time and energy. Now it's tough for me to not dive into the electrical engineering, which is not my specialty. I'm trying to focus on the programmer take here. So they're describing figure 2.6. Let's just go up there. You got your percentage of change, maxes out at 100%, not surprisingly. And 1 through 9 RC, you got a charge moment, and then you got a discharge moment here. So if we scroll down to see what RC is, it's not capacity and resistance. It's actually resistance multiplied by capacitance. In layman's terms, this is a simple unit of time. Interesting that they say that, and it's 1, 2, 3, 4 all the way to 9. And here's one of those aha moments as I'm reading, because it's talking about chips. If you look at DRAM, there's literal chips on there, and those chips have cells. And those cells have rows and columns, and that's a big aha moment for me. The next aha moment will come when I realize that there's problems with accessing. A program selects a memory location using a virtual address. The processor translates that into a physical address, and finally, the memory controller selects the RAM chip corresponding to the address. So what does a memory controller do? And it'd be great if you said, after the processor takes in the virtual address, it turns it into a physical address, then it hands it off to the memory controller, in which the memory controller will figure out which chip the address is on. Now to do that, only parts of the physical address are passed on in the form of a number of address lines. Let me summarize these two paragraphs by saying, because of this architecture with the rows and columns, chips would need to be demultiplexed for the address lines. A chip with 1 gigabit capacity would need 30 address lines and 2 to the 30 select lines. That's not 1 gigabit to the 6 or something. That'd make no sense. It is a footnote. Number 6 footnote says, and this is Draper speaking emotionally here, he hates those SI prefixes. So for him, a gigabit will always be 2 to the 30th and not 10 to the 9th bits. So that's a lot of bits. And let's try to summarize, kind of focus here. Again, we need this demultiplexer, which is an interesting idea, to pull apart the ones and zeros we need from the row address selection and that common address selection right there. Column, sorry, not common. I'm getting so intimidated by the electrical schematic, I can't even speak anymore. Well, those words right there, column address selection and row address selection, you'll see that in this format pretty much moving forward in the paper. And mind you, we're looking at a DRAM chip at a very high level right here. Now, pins of a chip are precious resources. It is bad enough that the data must be transferred as much as possible in parallel. So that's usually 64-bit batches, even in 2007. The memory controller must be able to address each RAM module, which is a collection of RAM chips. So what is a RAM module? A collection of RAM chips. If parallel access to multiple RAM modules is required for performance reasons, and each RAM module requires its own set of 30 or more address lines, and the memory controller needs to have, for 8 RAM modules, a whopping 240 pins, only for the address handling. So a picture's worth 1,000 words. Here's 240 pins for you to see. So I ask how many pins are needed for address handling, and this is the whole access section. So here's our summary. Do not worry if the details of this section are a bit overwhelming. The important takeaways are that there are reasons why not all memory is SRAM. Memory cells need to be individually selected to be used. The number of address lines is directly responsible for the cost of the memory. That is the memory controller, the motherboards, the DRAM module, and DRAM chip. Finally, we have a laugh out loud one. It takes a while before the results of the read or write operations are available. So that was a bunch of DRAM stuff, which there's reasons we're using that instead of SRAM, even though SRAM's faster. He says SRAM is currently used as CPU caches and on die where the connections are small and fully under control of the CPU designer. So a very wise man on Stack Overflow once helped me understand registers better. They're not just pins, they're pins connected to SRAM. So you may be asking, where's the protocol part of this access protocol? Well, I think it's right here in this paragraph. Basically, there are scalability problems that DRAM chips had, so this means the address is transferred in 2 parts. The first part will consist of addressing bits. We're going to say A0 and A1 in the example 2.7 over here, that real high level view. So if you notice, A0 and A1 is a row. This selection remains active until revoked. Then the second part, address bits A2 and A3, select the column. So I'll finish the video with this. Just describe the access protocol in your own words. In the next video, I'll go ahead and describe a DRAM access technical detail, so go a little bit deeper.